Right. But I'm not sure, I'm not able to upload all of them for some reason. I'm trying to upload, I'm not able to upload all of them.
Oh, yeah.
But there is a channel, you can subscribe to that channel and everything is available for that channel. Okay? Hmm? What do you mean like cats? Huh?
Your YouTube picture is cat.
Right. So what we saw last time was we had body M1, M2, right? This was R1, R2, and we had this as R. Okay? And this was our inertial frame, correct? Moving, non-moving frame. We had I, J, and K. Recall we had M1 R1 double dot is equal to G M1 M2 over R square U, correct? And M2 R2 is equal to minus G M1 M2 over R square. This is what we developed. And what did we prove last time? Remember what we proved?
The acceleration to 0 or something.
This acceleration of the center of mass is 0. The center of mass is a non-accelerating. See, this was. So this was RCG, right? Something like that. That's what RG. So this is center of gravity or center of mass. And we proved that RG is a non-accelerating point or inertial point. Okay? So you have this, let's call this A and B. So rewriting A and B, we have R1 double dot is equal to G M2 over R square UR. Correct? So what I did was divided the whole equation by M1. You want to sit there? Miss, I know you can see it. You sure? Huh?
I think it's this. Oh, is it? Y'all say correct?
Yeah, it's under the right way.
No, I can't.
You know you can. Okay, so I think everybody over here see the sun is like burning. No, I see perfectly.
Okay.
You're fine right there.
Or just, oh, you cannot do anything with that.
It's on the graph.
Yeah.
So you can keep writing.
Okay. So this is what you had, okay? Sorry, this is what you had. If we divide equation A by M1, you're going to get that, okay? And if you divide equation B by M2, you're going to get minus G M1 over R square into UR. Vector in the R direction. How did we define? Now this was R, right? Remember, R is defined as R2 minus R1. Since R is coordinatized in a fixed frame, in an inertial frame, you can just write it as R2 minus R1. Okay? The acceleration. Now, this would be minus G m1 plus m2 over m squared. Okay. We introduce, here we introduce mu as G m1 plus m2, which is the gravitational parameter. Okay, so your R becomes minus mu over R cubed. Does this make sense?
Only because I don't know where the X are. Where the X are come from.
There's extra R and then there's extra, this square became cube, right?
Just to cancel it. Okay, so the R divided by R cubed is R squared. What is R squared? So R over R cubed.
Here, UR, how is UR defined? UR is the unit vector, right? Because this is how UR is defined. If I just substitute that, we're going to get this. Okay, this is also written as plus mu over q. Please pay attention to this. This is a zero vector. Okay, so you have, I just moved everything to the left hand side. Let's call this C. C fundamental equation. Relative to body. And here are some notes which you need to remember about this equation. Second order. we'll take a minute to absorb this. You were able to follow this one, right? This we did last class, correct? This is what we arrived at the last class. Now, these two are obtained simply by dividing, see, cancel m1 on this side for equation A and m2 on for equation B, right? You can do that. And R, this, the relative position of m2 with respect to m1. You see that? Small r, vector small r, is the relative position of m2 with respect to m1. Do you see that in that sense? Okay. This r, since it is quantized in in a fixed frame, in an inertial frame, you can just write acceleration this way. Okay, so you have r. I think this was introduced last class, where r is equal to r2 minus r1. You have to go by vector. This is R1, R2, R. That is the reason, see, you have to understand vector map. This is the tail of vector R1, this is the head of vector R1, this is the tail of vector R, small r, this is the head of vector small r. That is the reason R2 is equal to R1 plus R. And that's the reason you get R is equal to this. Okay. So you have this, and if I just substitute R2 double dot and R1 double dot, you're going to end up with this. We introduce the gravitational parameter for a given body, for a given system of two bodies. This is going to be constant, right? G, M1, M2.
And G is the gravitational parameter or the whole thing?
G is the gravitational force. Mu is called the gravitational parameter. Okay. So mu is simply G M1 plus M2. Okay. And if we substitute back this mu in there, you're going to get this. And what we have done is, this is the unit vector UR, right? Unit vector UR is defined as vector R over its magnitude, correct? If I put back vector R over R, what are you going to get is over R cube, okay? And then if I take everything on the left hand side, you're going to get this equation, which is called the fundamental equation of relative two-body motion. This is very important. Again and again we are going to deal with this. Again and again we are going to encounter this. So please keep. This is the fundamental equation of relative two-body motion.
Relative to body motion.
Relative two-body motion. So why is it called relative two-body motion? That is because it governs the motion of M2 relative to M1. Okay? Keep in mind, we developed this with a inertial frame, right? This inertial frame. But in the universe, we don't know this R1 or R2 because we don't know where this point is. We developed it using this point, but now we have defined everything with respect to M1 and M2. This R, we got rid of this R2, R1 because we don't know this. You understand?
We don't know
we don't know where this point is, this inertial point in the universe, which is moving with constant velocity. Okay? But we said we'll assume there's a point, and we developed this equation. Now, everything is with respect to this r. The relative position of body m2 with respect to m1 will always be known. You can talk about this being Earth, this being Moon, this being Earth, this being some satellite, this being Sun, planet. Right? But if you cannot talk about this inertial point, Sun, Moon, because we don't know this.
So, just curious, if this is from the perspective of looking like, okay, where are we?
We are here.
Okay, so we're M1 in respect to.
Huh?
We're M1, and what we're looking at is M2.
Right. We are on M1 and we are trying to look at M2. Because in the absolute context, we don't know where this is. Anywhere in the universe, we don't know where this point is, where this reference frame is. But we will always know relative position, relative motion. That is the reason it is called relative to body motion. Okay? See, here one more thing you have to observe is R1, R2, R are coordinatized in this frame, I, J, K. What do you mean these are coordinatized in this frame?
Say that one more time.
Like,
R1, R2, R are coordinatized, okay, in IJK frame. What does that mean?
Using the IJK frame.
Hmm?
So if you're using the IJK frame, you can describe
The magnitude.
position of R1, R2.
What do you mean by coordinatized? The components are in IJK frame. Okay? But I can have another frame here itself at the same origin. And this could be coordinatized in this frame. What will happen? The components will change, right? So when we say coordinatized, the components are seen in this IJK frame. Okay? Got it?
the one that's seen in a different frame or the same frame that you referred to earlier?
The vector itself will be the same, but its components will differ based on what reference frame you're looking at. Okay? Think about velocity. The velocity by itself is independent of where you see it from. Correct? But if you're watching, for example, if you're going on the freeway, the relative velocity is different than absolute velocity. Correct? The velocity of a vehicle going beside you is much slower or much less faster than when you're seeing it from a fixed, staying at some point. So those are reference frames or coordinate systems. So you can have different coordinate systems. Okay? The reason we discussed that is, what we're going to say here is,
What does that say under it has two vector constants of
Hmm?
integration?
oh yeah, we did not discuss that. Yes.
No, I meant what does it say under it?
This one?
The next one,
Equation C,
above that,
each having three scalar,
oh, scalar.
constants. So you have this equation, right? This is a second order differential equation. what is your goal here? What do you understand the goal here is?
Are we still proving that the center mass is
No, we are done with that.
we're done with that?
What is the goal here? So, for example, this fundamental equation of relative motion is the most important. This is all you're studying in this course, okay? Think about it like that. The reason we have developed the whole concept of orbital mechanics is to study that. The reason you're studying so much math is because of that. Because people have tried to come up with ways to know that. So that is, if you're a space engineer, that is what is important to you. It's all about that fundamental equation of relative to body motion. Okay? Whatever math you're studying today, calculus, everything is an outcome because people have tried to study this for such a long time. A huge aspect of your life has been changed, has been impacted because people have tried to study this for this long. So you cannot forget this. You cannot forget this, you cannot forget this. If I ask you what is the fundamental equation of relative body motion, this should be at the back of your head. Okay? This is the governing equation. So what does this governing equation give you?
It gives you explanation of F1 and
Right. So what we are trying to study is relative motion of one body with respect to another. We are always interested in knowing where this body is, where this star is. Okay, with respect to our reference. And this gives you that. R, the vector R is the position vector of body M2. You can think about any two-body system in the universe. You can figure out the relative motion. So if you want to figure out the position of some of the other planet with respect to sun, how do you do that? So what we do, with respect to our reference, what we do is, we'll figure out where sun is in our reference, right? And then we'll figure out where the planet orbiting body is. So if I multiply, look at this equation. So this equation describes motion of body M2 with respect to M1. If I change this, R1 and R2, okay, would anything change? It is like multiplying this whole thing by -1. It will still remain the same. What that means is, the motion of this body, when seen from this body, is exactly the same as this body seen from this body. What it means is, you see, however you see moon from here, if you go to moon and see earth, it will exactly appear the same. Okay, so this relative motion, what we are seeing here is motion of body M2 with respect to M1, right? The motion of M1 with respect to M2 is also exactly the same. Okay, that is what this states. Because if we were to figure out R1 minus R2, everything would be just negative, negative, negative. So I would have multiplied this by -1, and you would still have the same exact equation. The solution would be the same exact solution. Okay?
Question. You said if you want to know where planet like other planets were in relation to the sun, you start with Earth and you go to.
Right. So what you would do is, now you know you're trying to figure out. Let's say you'll figure out motion of sun with respect to Earth, right? Because Earth with respect to sun or sun with respect to Earth is the same. You'll figure out Earth with respect to another planet. Now you can link both of them, right? And figure out what is the motion of. Got it? So the intent is, again, the intent here is to study the motion of an orbiting body with respect to a central body. One body with respect to another body. The motion, the position, the velocity, the acceleration, all those. Okay? So this equation gives you that study, that the answer to that question. This is a big answer to that question. Now what happens here is, if your goal here should be to find an expression for R. What do you do when you're given a second order differential equation? You will try to solve for the variable x, right? So if you were to do that, you could simply do that by integrating this whole equation twice. You have double derivative, right? If you integrate this equation twice, you're going to get a value for R, right? What that means is, if we don't give the initial conditions, the integration will result in a constant, right? Constant of integration. The first time we integrate, we'll get one constant. The second time we integrate, we'll get another constant. It will have two constants, two vector constants, because this is a vector. So this is actually three differential equations. R1, R2, R3. Correct? The components. So if you integrate it twice, you're going to have 6 constants, and that is what it says. It has 2 vector constants of integration, each having 3 scalar constants. In total, there are 6 constants of integration involved in solving this equation of motion. Okay? What we now do is, you have this M1, this R is the same. We introduce a reference frame here. This is small I G K, okay? And this is still R. Think about Earth and let's say a satellite, okay? Where would the center of gravity of that system be? Huh? If you're thinking about Earth as a homogeneous sphere, where would the center of Earth be? At the center, right? So if you add a small satellite here, would that center of mass change? It will not change much. Correct? So you can say we will use this reference frame which is attached, which is on the bigger mass to measure this R. And this way we get rid of this reference frame as well. We have proved that the center of mass of this system is a inertial point. So the origin of this reference frame is also an inertial point, right? If we have proved that, if we know this, we can apply Newton's laws, right? We don't have to use this now. We proved that the center of mass of these two systems are the same, and we assume that the body with a larger mass is a spherically homogeneous mass, which means its center is at its center of mass is at its geometrical center, right? And we have already proved that the center moves with a constant acceleration. It's a non-accelerating point or an inertial point. If we attach a reference frame to that reference frame will be an inertial reference frame. And the motion of anything with respect to that can be studied or can be analyzed using Newton's laws of motion. Okay, and that is what we are doing. So this is M2. Now, R is measured in terms of xi plus yj plus zk. Okay. Understand here, everything was, for example, here R would have been x I plus y j plus z k. All these would have been coordinatized in ijk frame. Here everything is coordinatized in a small ijk frame. Okay, and we can conveniently define this reference frame for ourselves. We don't have to worry about assuming that this reference frame exists somewhere.
Okay, 3 questions. First one, we chose that point M1 arbitrarily because both center masses are the same. We just chose M1 because we know that everybody knows. Is that correct?
Say that again.
We chose point M1. We chose the mass M1. Off of what you stated earlier, the center masses of the two are the same. So we chose M1 because we know practically everything about M1 because that's our known point. Is that correct?
You mean between M1 and M2, we have chosen M arbitrarily, that's what you said?
That's what I said.
Right, so let's do the assumptions. I think assumptions will make things clear. When we do, the assumptions are M1 is much greater than M2. Make sense? Which means everything is in and around M1. Okay? 2, M1 is spherically homogeneous. You understand what spherically homogeneous is?
Yes. A perfect sphere or something.
Right. Perfect sphere with then everything is distributed homogeneously. It's a perfect thing. And 3, of course, this I think gravitation is the only force acting on it. Is the only external force. So this is called this motion is called Keplerian motion. Keplerian motion.
Copeland.
Kepler.
Keplerian.
Oh, okay, I see what you're saying.
Jonas Kepler. Okay, because the only force acting is gravitational force. If you're studying, you cannot study the motion of aircraft or something which is in much lower orbit using these equations. For example, think about something which is about 20 or 30 kilometers or miles from Earth. The atmosphere is really thick in that region. So the atmospheric drag is very significant. You cannot study motion as Keplerian motion in that space. You have to be at least 120 miles above the surface of Earth to study Keplerian motion. Even then, there is some atmosphere even there, but that is considered to be outer space, 120 miles above the surface of Earth.
120 miles or 120K?
120 K, I think.
62 something, 60 something miles, right?
80,
Okay, yeah, 80 miles. Yeah.
but something like that. Okay? You understand what Keplerian motion is? There is no other external force acting on influencing the motion.
Does that drag?
That's drag, yes. And see, if you really think about it, it's not just the atmospheric drag. There is solar drag. Okay. There is
Antimatter drag.
there is magnetic activity which can produce a drag.
So, solar drag?
There is solar drag. If you heard about solar sails, how do solar sails travel?
It's this guy who goes from door to door and he wants to sell you sunshine.
So that
So solar sails just use, huh?
you feel like a photons pushing the
Right. So you can actually see these solar sails. You can use a solar sail to gradually go to another planet without any energy at all. You can just use a huge solar sail to translate through space and go to another planet.
How fast is that approximately?
It depends on how big your surface area is.
I don't know the rate when that.
Huh?
Are there solar cells in space right now? So we can just look it up.
It is really quick. How's it working? How's it working?
It just uses solar pressure. So when you those photons, when
Radiation.
solar radiation hits, what is radiation? It's actually photons traveling, right? So that there are some particles traveling. So if you expose a huge surface to that, it is like hitting solar pressure.
I don't think you can call it photon particle.
That's another discussion, but what's happening is something can get affected by solar drag or solar pressure. Okay? So we'll stop here. Please keep this in mind. Now, if you are asked to develop relationship for acceleration velocity based on this, you have done this.
Are you going today?
Right?
Where are the tutors? What are you doing?
You have done this. Correct? If you are asked to develop relationship for an inertial frame or a non-inertial frame, this frame ijk, the small ijk, could be a inertial frame. When we talk about inertial frame, we talk about Earth-centered inertial frame. And this could be a non-inertial frame, which means it could be Earth-centered fixed. Something which is fixed to Earth will rotate with respect to Earth. If it is rotating with respect to Earth, that is not a inertial frame, it's a non-inertial frame. So if you are asked to develop the kinematics of that, either in an inertial frame or a non-inertial frame, you should be able to do that as omega, where omega is the angular velocity of Earth itself. Okay, got it?